This video is intended for beginning X-ray students or to use as a review. It presents a basic look at radiographic detail and the fundamental causes of detail seen on all radiographs. The basic definition of detail or resolution is fairly simple. On its most basic level, detail describes the ability of a radiographic image to record small objects. The higher the level of detail, the smaller the object that can be recorded. When one considers the range of things that will affect detail, these changes have one thing in common. They're all geometric in nature. If a change is not geometric, it doesn't affect detail. If one examines the word geometric, we first notice the prefix geo. Geo refers to the shape or configuration changing in some fashion. The configuration of the X-ray system must change, specifically the tube position, the source to image distance, the image receptor, again the source to image distance, or the patient needs to move or rotate, changing the object to image distance. The suffix of geometric is metric and indicates that the size of something changes. Sizes that change could range from a change in the size of the effective focal spot, to the pixel size, to even the size of the object being radiographed. Regardless of your efforts to minimize detail loss, all radiographs will suffer from some degree of detail loss. Here is a device for measuring detail. It's called a resolution grid. The resolution grid is a 2-inch square of lead foil embedded in plastic. Inscribed in the lead are progressively thinner spaces and lines. In this grid, the spaces range from 0.6 lines per millimeter to 5 line pairs per millimeter. The more line pairs per millimeter recorded, the higher the detail or resolution of the X-ray image. Here is a second image. Notice anything different? If you were to conclude that it looks blurrier than the image on the left, you're correct. Examine the image on the left and ask the question, which group of bars are the smallest bars that I can see on the object? To my eye, I can see distinct bars all the way to 3.1 line pairs per millimeter section of the left-hand grid. On the right-hand grid, I can see bars to about 1.8 line pairs per millimeter. While you may not agree with my exact measurements of detail, you can agree that the sharper image on the left records more detail and appears sharper. When one considers digital imaging, it is fair to say that digital systems do not record as much detail as film screen systems did. A digital system records from about 4 to 20 pixels per millimeter. Here is a 30 millimeter scale, and here is 1 millimeter from that scale. On an AGFA CR system, a 10 by 12 inch plate records detail at the rate of 10 pixels per millimeter. This means that each pixel is 1/10 of a millimeter square. A 14 by 17 inch plate records detail at a lower resolution of 6 pixels per millimeter. You will find that most DR plates capture at a rate of about 6 pixels per millimeter to 3 pixels per millimeter. Mammography requires an unusually high amount of detail, and mammographic plates capture at about 20 pixels per millimeter. So detail is measured in line pairs per millimeter. How does this equate to the pixels on a digital plate? In the past, film screen technology would capture at a rate of about 10 to 20 line pairs per millimeter. We can roughly estimate the resolution ability of a digital system by taking the pixels per millimeter and dividing by 2. So a 6 pixel per millimeter plate would resolve at about 3 line pairs per millimeter. Of all forms of detail loss we will discuss today, motion is the most detrimental. Motion is easily controlled by first using your people skills. Give all patients a good idea of what you intend to do before you do it. Plan ahead and help the patient by explaining the exam and by supporting or immobilizing the part. Finally, use short exposure times if possible. If motion does appear on an image, this is a clear reason for a repeat exposure. Be sure to make necessary adjustments to your procedure to assure that there's only one repeat. Now let us look at non-motion aspects of the imaging system that relate to detail loss. The focal spot has a definite size. X-rays are emitted from the top of the focal spot and the bottom and all points in between. These rays have a unique perspective when projecting an image and don't agree as to its exact location. Hold your finger about a foot in front of your face and close one eye. Then switch eyes. Notice how your finger changes its apparent location. The finger doesn't move, but rather your perspective does, just like rays projected from the top and the bottom of the focal spot. Modern X-ray tubes have focal spots that can vary from 0.3 of a millimeter to about 2 millimeters. The most popular sizes are 0.6 to 1 millimeter. Remember, the smaller the focal spot, the higher the detail of the image will be. Most electromagnetic radiation diverges from its source, which means they spread out in a predictable manner, and the further they move, the more they spread. If we are considering an X-ray beam that impinges upon a flat surface like an imaging plate, the beam will spread along its width as well as its length. For this illustration of effective focal spot, I will use a stationary anode because it's easier to draw. It is made of copper and has a small tungsten target embedded in its face, protected from melting. The focal spot is a small area where an intense electron beam is projected to produce X-rays. The effective focal spot is projected perpendicular to the long axis of the anode and ranges in size from 2 millimeters to 0.3 of a millimeter. Here is a perspective where you're looking up from below the anode with your eye centered on the central ray. This is a representation of the anode, the patient, and the image receptor below the patient. The dot represents a small object that we want to project onto the image receptor. When we project a ray from the top of the focal spot, the ray projects the image to a point to the right of the actual location due to the divergence of the ray. A ray from the bottom of the focal spot projects the image to a point further to the right. Remember that there are multiple rays projecting between these two rays that do not agree as to the point's exact location. Magnifying the image projected onto the plate shows the points spread over an area of the plate with a larger periphery and a darker center. The lighter peripheral area is called the penumbra and is described as the area of image and sharpness. The darker center is called the umbra and more closely represents the size of the original object. In the future, you will be asked to recall several facts regarding detail. More importantly, as a radiographer, you will end up in situations where maximizing detail is important. This knowledge is the first step in understanding how to achieve maximum detail. The more detail an image has, the smaller the object recorded. This may be important for hairline fractures or for looking for kidney stones, as an example. Small details may not be visible on your computer monitor. That's why I will spend a few minutes differentiating detail from visibility of detail. Small details may not be visible because they blend in with the background anatomy. Computers may enhance detail in this case. Also, radiologists may further enhance visibility of small details by manipulating window width or level. Most monitors sold with radiographic imaging systems are not of diagnostic quality. Monitors used by radiologists are up to diagnostic standards and resolve at a much higher detail level. It has been my experience that practicing radiographers are not concerned with detail, but rather visibility of detail, sometimes confusing the two. They will ask, if I can't see it, what good is it? That's a very practical question. Understanding the difference between detail and visibility of detail is crucial for a student radiographer. Detail is affected by changes in geometry and geometry only, whereas visibility of detail is affected by a much wider range of changes. Again, technologists are concerned with maximizing details and making them visible on a radiograph. Anything that affects detail will affect visibility of detail in the same manner. So any change that is geometric will affect the visibility of detail. Changes in density will affect visibility of detail. Since density can be altered by changing window and level, some density errors may be fixable. Underexposure in a digital system is a bigger problem than overexposure. When a digital image is underexposed, a graininess will become evident. This graininess is called quantum mottle and is best fixed by repeating the image at a higher MAS. Overexposure is less of a problem. Most modern DR and CR systems can correct overexposure to a point. With large overexposures, image saturation may occur, where structures that should be dark gray appear as black and blend in with the background anatomy. Additionally, overexposure contributes to increased patient dose. Contrast allows people to discern objects from their background. The higher the contrast, the easier it is to see the object and separate it from background densities. P level used to play a pivotal role in contrast formation. In digital radiography, KVP has less an effect on the contrast one sees in the final image. With that said, KVP still plays a role in the contrast a computer needs to determine the difference in density between adjacent pixels. So overall, high KV images will demonstrate less visibility of detail. Anything that contributes to or reduces fog formation will affect visibility of detail. Collimation not only prevents fog but also reduces dose to the patient and anyone assisting the exam. Grid's primary function is to reduce fog, and finally, patient composition plays a role in the formation of scatter radiation that contributes to fog. Thank you. This will end my introductory presentation of the foundations of detail. Thank you for your attention.